In this part of the video, we would like to find the solution of this differential equation with an initial value using Euler's method. As we have discussed before, to solve any differential equation means that we are asked to find the function y, which is the integrated version of this differential equation. In order to do that, we have few clues at our hand. One is the initial value, another one is the first derivative of y in this format. So using these two clues, we would like to find the function y, and in Euler's method, we are basically trying to plot the graph of y in the graph. So now we will first use the first clue that is at our hand, that is initial value. If you look at the equation closely, here you will find one clue is given in the form of initial value, that is at x equals to 0, the value of y would be 1. We can plot this point in the graph like this. Now we have something in our hand, and in this way we have to plot few values of y at regular interval. For our case, we have thought the regular interval or the step size to be 0.5. So now our goal is to find the value of y at x equals to 0.5, and here we will use the clue, second clue, that is first derivative of y. Using this second clue, we are now trying to find the value of y available at 0.5, and let's see how we can do that. As you can see, there is a function given to us which is the first derivative of y, the function that we are trying to form. If we plug 0 into this function, we get as a result 1. What does it mean? It means that if we draw a tangent on the function y at x equals to 0, the slope of the tangent would be 1. And using this very clue, we are now trying to find the value of y available at x equals to 0.5. How we can do that? This is the equation. So the new value of y can be calculated using this formula. The old value will remain where it is, plus if we multiply the slope into the step size, that will give us the new value of y. Here the new value of y would be 1.5. If you look closely what we have done here in the triangle, you can see the slope has come out to be 1. What does it mean? It means that the ratio of height and base here is 1. And now if you multiply this slope with the base, which here is a step size, you get reach to this point by following this slope. This is what exactly we have done here to find out the new value of y. Now let us find another value of y which is available at x equals to 1. So in order to do that, we need to find the slope available at 0.5. The slope available at 0.5 is 0, and thus if we run the formula of finding out new value of y here, this is what we get, which means the value of y will remain unchanged even at x equals to 1. Using similar logic, we will now look to find the value of y available at x equals to 1.5. So in order to do that, we will again need the value of slope available at 1, which is here 0, which means at 1.5, x equals to 1.5, the value of y would still remain unchanged. So this is how the value will stay. In similar fashion, now we are looking to find the value of y available at 2. So we need the value of slope available at 1.5, which here is not 0, here is 1. And now if we plug values into formula, here we get the value of y available at x equals to 2 is 2. So in this way, if we keep running our iterations and keep finding out values available at certain interval, this is what we get to see. See here, we have found out values of y up to 3 and plotted it in the graph, and this green line is the exact function of y. You have seen it in previous part of the video. So here you can see, using Euler method, we can reach to reach much closer to the exact function of y. So in this way, using Euler method, we can solve any differential equation intuitively, and thus we can come to a conclusion that we can construct the function y that is given to us in the form of a differential equation. So using Euler method, this is how we can solve any differential equation. Thank you very much.